Welcome to Dhirendra Digital Solutions, your learning partner. Hello friends, today we are going to discuss about digital electronics. Now, there are two important words that you can see in this name. One is digital, the other part is electronics. Now, we all know what electronics is. It is all about building a circuit wherein we are going to design the required results, or we are trying to obtain the required results. Whereas when we say digital, we are talking about a binary level of understanding. Either the data can be in the form of 0 or it can be in the form of 1. So, whenever we talk about any information being communicated in the form of zeros and ones, we call it as digital electronics. Now, in many cases, the same content would be delivered with a name logic design. And you would have also come across something like digital electronic circuits, or you would have also come across a terminology called as digital circuits and logic design. Now, all these four names mean one and the same. They'll be touching upon the very much the similar concepts. Now, why do we call this as logic design? We call it as logic design because we are going to implement certain designs with the help of the logical understanding that we have on the concepts. Hence, we call them as logic design. Now, digital electronics, similarly, we have digital electronic circuits because we are into designing and building circuits. Similarly, digital circuits and logic designs is pretty much evident that these are pretty much the same names. Now, in this subject, we'll be talking about the data in the form of two levels. One is called as the 0 and the other one is 1. And hence, this is always known as the binary number system. Now, why do we call it as binary number system? The reason why we call it as binary number system is we have logical zeros and logical ones. It is all about the voltage levels. For a logical zero, we consider zero voltage to be logical zero, whereas logical one will be represented by 5 volts. This is the standard that we have been following. 0 volts and your logic 1 will be represented by 5 volts. Now, since there are two states, we have called it as binary. Now, to start with, the most important thing that we have to work with is going to be understanding what is binary number system. Right from the beginning, maybe in our fifth standard, sixth standards, we have started off with the basis or the number systems. But still, the understanding and conversion of these number systems is extremely important. And how are these number systems being generated is also very much important. Most of the times, we generally tend to lag the understanding of the number systems and try to understand things only from the outer perspective or directly jump into the digital circuits. So the first thing that we're going to do is going to focus on trying to understand what is number system, how are different number systems being evolved, and what are the number systems that are being used in our day-to-day life in terms of digital systems. As we all know, one of the most primary number system that we have always been working with since our school days is decimal number system. Decimal number system. This is the most common one, wherein we have numbers ranging from 0 to 9. Whereas when it comes to digital electronics, we will be talking about binary number system. As I have already told you, that binary number system talks about only two values, which is 0 and 1. Then we have something called as octal number system. Now, what does octal number system stand for? It stands for 8 different characters that are existent, which is going to be between 0 and 7. Now, similarly, there is one more number system called as hexadecimal number system. Now, here we have numbers ranging from 0 to 9, and since we are saying hexadecimal, there are going to be 16 different characters. The 10 characters 0 to 9 are borrowed from the number system, whereas the remaining 6 characters are being represented by the alphabets A to F. So this makes a total of 16 characters. Now, the most important thing is, how are these number systems being converted into one to the other? Now, to start with the conversions, whenever we talk about conversion, the first number system conversion that is being always taught is decimal to binary and binary to decimal. However, we have been studying the binary to decimal and decimal to binary number system conversion since ages. So when we start with decimal to binary conversion, we are talking about, say for example, let us take 19 as number. Now, to convert this into binary, we will first factorize it by 2. So when I factorize this 19, 19 becomes 9. 9 into 2 is 18, plus 1 is the remainder. Now, factorize this further, so you get 4 and 1. Since 4 is still greater than 2, so go ahead with factorization. 2, remainder is 0. And now, when we factorize it further, we get 1 and 0. The numbers are always read in this order. So, the decimal number 19, which can be represented as 19b, is equivalent to 1, 0, 0, 1, 1, and write it as b, which is binary, or this 19 can also be written as 19 to the base 10. Similarly, this can be written in binary as 1, 0, 0, 1, 1 to the base 2. Either you can use base 2 representation or B representation, D or decimal. They're all one and the same. Now, this is what we have been studying since our school days. Similarly, we would be studying the binary to decimal conversions. Say for example, I would take a number like 1, 0, 1, 0, 1, 1 binary, which is to be converted into decimal. Now, when you take this, what we do is we multiply each of these digits with its weight. Now, over here, it is going to be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 3, 4, and 5. So we get 1 into 2 to the power of 5 plus 0 into 2 to the power of 4 plus 1 into 2 to the power of 3 plus 0 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus last digit is 1 into 2 to the power of 0. Now, what is this equal to? 1 into 2 to the power of 5. What do we mean by 2 to the power of 5? 2 into 2 is 4, 4 into 2 is 8, 8 into 2 is 16, 16 into 2 is 32. So 2 to the power of 5 is 32, plus 0 into anything is 0, plus 1 into 2 to the power of 3 is 8, plus 0 into 1, 0 plus 1 into 2 to the power of 1, which is equal to 2, plus 1 into 1. This will be equal to 32 plus 0 plus 8 plus 0 plus 2 plus 1. 32 plus 8 is 40, 42, 43. So this is equal to 43 in decimal. Either you write it as 43D or you can write it as 43 to the base 10. Either of the representations are correct. Now, here we have seen how to convert the numbers from one number system into the other number system. Now, having studied this, the most important concept that is important for us in digital electronics is signed numbers and unsigned numbers. When we say unsigned numbers, we have been studying as school children unsigned numbers. We have been studying them from as school students when we start with 1, 2, 3, so on till 9, and then we have 10, 11, 12, and so on. We talk about only positive numbers. But as we grew, we also started to understand the signed numbers. We started looking to signed numbers. Then we said 0 is going to be the midpoint. Anything that we have on the left hand side is going to be -1, -2, -3, and so on. On the positive side, we started talking about +1, +2, +3, and so on. So here we got into the concept of the signed numbers. Same way, when we talk about binary number system, we also talk about the signed numbers as well as unsigned numbers. Now, let us look at how the signed numbers and unsigned numbers are represented in digital electronics, in binary number system. The positive number is always represented by a 0 and the negative number is always represented by 1. Now what do we understand by this? Any binary number when written can mean two different things. Say let us first start with unsigned numbers or unsigned representation. Say we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Now, if I keep writing it this way, it is going to take ages for me to write. So what we do is, I'll just append 4 more zeros over here, 4 ones, then 1, 1, 1, 1, 1, 1, 1, 1. Here I'm going to have 0, 0, 0, 0, 1, 1, 1, 1. 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, and here it's going to be alternative zeros and ones. Don't worry, all the 16 numbers have been covered up, right from 0, 0 to 1, 1, 1, 1. Now, if I take this as the binary representation, or I can put this as binary representation, and for unsigned numbers, this will be represented as 0, this is represented as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 for the unsigned numbers. Now, the same representation has been split into two parts. This bit is called as the sign bit. That is the most significant bit that is being represented. The most significant bit. Remember, bit is equivalent to digit. In case of decimal number systems, we call them as digits. In terms of binary number systems, we call them as bits. Now, the most significant bit, the first bit that you have written, is called as the sign bit. The rest of the bits that we have over here are called as the magnitude bits. Magnitude bits. These will decide the value. This will decide the positiveness or the negativeness of the number. So if I use this particular standard to represent my signed numbers, if I use this technique to represent my signed numbers, what we find is this becomes, this is 0, so it is plus, and we have 0 because 0, 0, 0 gives us 0. Then plus 1, this will be plus 2, this will be plus 3, plus 4, plus 5, plus 6, plus 7. It is pretty much the same as far as the positive numbers are concerned. But now, when it comes to negative numbers, what we see over here is this is indicating a negative value and the magnitude is 0. So we get minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and minus 7. Now, what is the problem with this? The problem is we do not have a positive 0 and a negative 0. It is only a 0. 0 is neither positive nor negative. But what we find in this particular representation is there is plus 0 and minus 0. Since we cannot have two different zeros, what we said is we are going to replace this with one value addition, one additional value. Now, before we get into one additional value, there is one more very significant problem with this representation. What is it? Say, for example, if I add 1 to the 0, I get 1, 2, 3, 4. If I'm adding 1 to each one of them, I'm getting the next number. Now, if I add 1, 1, 1, 1 with 1, the result that we get is 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1, 1 plus 1 is 0, carry is 1, and 1 plus 1 is 0, and the carry is 1. Now, if I look at only these 4 digits, these 4 places, then it is the first number itself. That means whenever you overflow from the largest possible number, you will go back to the least possible number. This is a cycle. Now, if you look at the numbers over here, it keeps on incrementing 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. And what is the smallest possible number here? The smallest possible number is minus 7. But the next representation is minus 0. So the problem is this number system is not forming a cyclic loop. Similarly, if I keep on decrementing over here, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0. From 0, I should have gone to plus 0. Then we get 1, 2, 3, 4, 5. So it becomes a cycle. This particular cycle is not existent in this particular number system. Since this number system is not having the cyclic formula, just like you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, After that you have 10. So having 10 indicates your digit has become 0. The 9 has become 0. So similar cyclic loop is important in case of number systems. If that is not existent, then that number system cannot be used. So what we did, we said we are going to use this representation for the positive numbers. There's no change, so we'll retain that. But to create the cyclic loop from plus 7, which is the largest possible number, I should move on to the lowest possible number. So we started representing numbers in such a way that we retained this as plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and here we decided to use this representation of 1,000 as minus 7. This will be minus 6, this will be minus 5, this will be minus 4, minus 3, minus 2, minus 1, and this is minus 0. Now, if you look at this, there is a complete cyclic loop that is being created. From plus 0, you will go to minus 0, or from minus 0, you will go to plus 0, plus 7, the next representation is minus 7, minus 7, if you go back, you will get plus 7. So this is properly in the cyclic format, and hence this representation is called as the ones complementary number system. Ones complementary number system. Why do we call it as ones complementary number system? Because if the number is negative, then take complement of the number. Wherever you have zeros, replace it with ones, and ones have to be replaced with zeros. This is how we generally come up with complements. So zeros, if you replace it with ones or here, so it becomes 1, 1, 1 as far as magnitude is concerned. So magnitude is 7. Since this is 1, we have taken the complement of the numbers and the value becomes minus 7. Similarly, 0, 0, 1 becomes 1, 1, 0 upon taking complements. So this becomes 6. 1, 1, 0 is 6. It is a negative number, so minus 6. Similarly, we have got it. So we have replaced all the zeros with ones to get the magnitude component. Hence, we called it as ones complement. We've taken just a complement of the number. But remember, there was one more problem that we had spoken about. That is the plus 0 and minus 0. Two zeros existent. Now, this was one of the problems which still continued with one's complementary number system. So, this problem was being eliminated by adding a magnitude extra to the negative side. So, the positive side remained the same, wherein we call this as plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and this minus 7 became minus 8. The representation was being changed over from minus 7 with an additional value of 1. So this became minus 8. So with this added value of 1 in terms of the representation, minus 7, minus 6, minus 4, 5, minus 4, minus 3, minus 2, and this became minus 1, and plus 0 was considered as 0. So this becomes the representation. Now this number system is called as 2's complementary number system. This is called as 2's complementary number system. Now, having a thorough understanding of how the number system is being generated is very important for us. Only after understanding why the number systems are two of them, which is one's complementary number system and two's complementary number system that is being used, and not directly the sign bit and the magnitude bits are being used to represent the numbers is clear. Now, let us look at the reason why we started looking at octal number system and hexadecimal number system. Now, when we look at microprocessors, we started looking at 8-bit microprocessors, 16-bit microprocessors, and so on. Now, if we look at this number, wherein we have got 8 bits, total of 8 bits gives me 2 to the power of 8, which is equal to 256 combinations. Now, when it is giving me 256 combinations, it is difficult for us to remember as to 0, 1, 1, 0, 1, 0, 1, 1, what is this particular combination for. So what we did is we started to group them as a group of 3. When we started to group them as a group of 3, this becomes 7, this becomes 6, and this becomes 1. So 167 to base 8 is the representation that we started looking at. Now, why is that we are talking about octal number system here again? And what are the range of numbers? When I say 0, 0, 0, this is the lowest possible number, which is represented by 0, and the largest possible number is represented by 111, which is equal to 7. So, a total of 8 different numbers are available in this particular number system. Hence, whenever we talk about the binary number system, we always talk about converting it into octal number system, and this is how the entire octal number system came into existence. Now, as I've already told you, it is very easy for us to convert any number from binary to octal or vice versa. The reason being, you write any number of your choice and just start grouping them as a group of 3. So this becomes 6, this becomes 6, this becomes 2. So this is equivalent to 1 0 1 1 0 1 1 0 to the base 2 is equivalent to 266 to the base 8. Remember, we can also represent this as 266 to the base O. O represents octal. Similarly, this 2 can be replaced with B that we have seen earlier. Now, this is about binary to octal conversion. And in case if I have to perform a octal to binary conversion, the process is again going to be simple. Say I have a number like 372 to the base 8. So this will be equivalent to 3 is represented by 0, 1, 1. Then 7 is represented by 1, 1, 1. 2 is represented by 0, 1, 0. So this is to the base 2, or you can write to the base B. So this is 3, this is 7, this is 2. So this is how you convert a number from binary to octal and octal to binary. Now, as we went on with the higher order number systems or higher configured processors, instead of 8-bit, we started looking at 16-bit, 16-bit to 32-bit, 32-bit to 64 bits, and so on. Then the grouping of 3s was not becoming so easy enough to work with. For example, if I give you a number which is 16-bit, like this. Now, even if I'm trying to group them in the form of octal, 1, 2, 3, 4, 5, and 6. There are 6 characters that are coming in. Now, when we say 6 characters, it is again going to be difficult for us to remember or recollect. That is when we started looking at, instead of grouping 3 numbers, we'll start grouping 4 numbers. What happens if I group 4 numbers? What happens when I group 4 numbers is, this is 1, 2, 3, and 4. Remember, all our processors are either 8-bit, 16-bit, 32-bit, 64-bit, and so on, which are multiple of 4. So grouping 4 digits together or 4 bits together was going to be more relevant to us. Hence, we started grouping them as 4. When we started grouping them as 4, for the number representation, we had 0 to 9. 10 characters were available. So we were running short of 6 more characters, because when we say 0000, which is the lowest possible number with respect to 4 bits, the representation is 0, whereas 1111 gives me a value of 15, which is equivalent to total of 16 characters. So we had 0 to 9, 10 characters were available, we were running short of 6 more characters. So we borrowed A to F from the alphabets to represent numbers. So that is how your hexadecimal number system will have 0 to 9 and A to F. Now, if I start grouping these as 4 of them, 4 bits at a time, now 1 0 1 0 would be represented as A, 1 0 1 1 will be represented as B, 1 1 0 0 will be represented as C, 1 1 0 1 will be represented as D, 1 1 1 0 is represented as E, and 1 1 1 1 is represented as F. 0 to 9, we already know the representation. So the remaining 6 representations were being put across like this. So 1100, what is 1100? 1100 is C. So this becomes C. Then 1101, 1101 is B. 1100 again is C. Then 1110 is E. So this becomes E, C, B, C to the base 16, or you can also write it as E, C, B, C, H. Both the representations are acceptable. Now, this is how you convert a binary number into hexadecimal number. You have started grouping those bits in the form of 4. Now, in case if you have to convert a number from hexadecimal to binary, then it's going to be very simple. Say for example, 1, 2, A, E is the number that I want to have in hexadecimal, which I want to convert it into binary. So 1 is represented by 0, 0, 0, 1. Then 2 is 0, 0, 1, 0. A is 1, 0, 1, 0. And E is 111, 0 to the base 2, or you can write B. So this becomes my binary representation for 1 to A. So this way we convert your binary numbers into hexadecimal numbers and hexadecimal numbers into binary numbers. It's a very simple process of conversion. Now that we have looked into one's complement and two's complement, in binary number system we have one's complementary and two's complementary number systems. Now, what do we mean by one's complementary number system? We have replaced zeros with ones and ones with zeros. Now, in general, whenever we start with understanding complements in binary number system, anyone will tell you zeros has to be replaced with ones, or ones have to be replaced with zeros to get the complements. But the matter of fact is, complements are not defined by replacing 0 with 1 or 1 with 0. It is just that in binary number system we have only 2 numbers. So 0 complements 1 and 1 complements 0. We don't have any other number. So we feel that replacing zeros with ones and ones with zeros is finding complements. Now, if we take up our decimal number system, Then, in case of decimal number system, we have total of 10 characters 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now in this case, we have to understand that 0 complements 9 and 9 complements 0. Similarly, 1 complements 8 and 8 complements 1. 2 complements 7, 7 complements 2, 3 complements 6 and 4 complements 5. Now, you would be able to see that the smallest possible number in the number system is complementing the largest possible number. Now, why is that we call these numbers as complements? Say, for example, I have some structure like this. Now, in case if I ask you what is the complement of this structure, you will immediately come up with structures something like this. You would say this complements this, and similarly this complements this, because it is helping. When we combine these two, we find that they become a perfect square or a perfect device. Similarly, when I add 0 with 9, the end result is the maximum value, which is 9. 1 with 8, it is 9. 7 and 2, it is 9. 3 and 6 is 9. 5 and 4 is 9. So, the numbers complement each other. Complements are the ones which combine together to form the total value. So, if we look at binary number system, we find that there are only two numbers. The largest possible number is 1. So, adding 0 with 1 will give us 1, and similarly adding 1 with 0 will also give us 1. That is why 0 complements 1 and 1 complements 0. Now, similarly we can see it in decimal number system. Now, next when we look at the octal number system, we have the sevens complement. When we talk about octal number system, we have sevens complement, and in case of decimal number system, we call this as nines complement. We call this as nines complement. In case of octal number system, we have total of 8 characters. So 0, 1, 2, 3, 4, 5, 6 and 7. So what will be the condition over here? What complements 0? The complement of 0 is 7, and 7 complements 0. Similarly, 1 and 6 are complements. 2 and 5 are complements. 3 and 4 are complement to each other in case of your octal number system. Similarly, when we look at hexadecimal number system, or in short, we generally write it as hex or hexa. Now, when we talk about hexadecimal number system, we call it as 15's complement. Now, here we have total of 16 characters: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F. Now, what happens over here? 0 complements F, F complements 0, 1 and E are complement to each other, 2 and D, 3 and C, 4 and B, 5 and A, 6 and 9 and 7 and 8. Since the total value is ending up with 1, we call this as 1's complement. Since the total value is ending up with 9, we call it as 9 complement. Total is ending up at 7, 7's complement. Total is ending up with 15, so 15's complement. Now, in binary number system, we have seen one more component, which was 2's complement. How did we obtain 2's complement? We obtained 2's complement by taking 1's complement plus 1. That is for eliminating the minus 0 and plus 0 problem. Similarly, when it comes to 10's complement, we will also find 9's complement over here plus 1 to eliminate the problem of minus 0 and plus 0. Similarly, in octal number system, we have something called as 8's complement. When I say 8's complement, we find 7's complement plus 1. And here we have 16's complement. When I say 16's complement, it is basically finding 15's complement plus 1. So this way we will be able to end up with all the different number systems. So we have 1's complement, 2's complement in binary number system. In decimal number system we have 9's complement and 10's complement. In octal number system we have 7's complement and 8's complement. And finally, in case of hexadecimal number system, we have 15's complement and 16's complement. So this sums up the entire number system. Thank you. Please do comment, like, share and subscribe. For more related videos, log on to www.dhirendra digital solutions.in. The link is available below.